You can see my screen, right?
Yes.
I'll start then. So in this class, we'll be discussing VP. So this is like a very important idea in number theory in general. So like looking at the exponent of a prime in the prime factorization of a number, that is a very helpful and important idea in a lot of problems. So first, we'll be defining the function VP, and then we'll be looking at some basic properties. So the way VP is defined is first we'll define VP um, from naturals to the non-negative integers. Um, so the way it's defined is we consider a particular prime P, and for every natural number n, we define the set SP comma n as all non-negative integers k such that um, k is a non-negative integer and p to the power k divides n, and then vp of n would be equal to the largest element um, in this set sp of n. So essentially it's the you consider the prime factorization of n, and then you look at the exponent of p in the prime factorization. So for example, um, what would v2 of 20 be? um, Hello, can you hear me?
Please,
Yeah.
you're audible.
Yes. So like, can you like unmute and say
Two.
hello? Two. Yeah, exactly. V2 of 20 is 2. And so then so now VP is already very helpful in a lot of problems where it is not very easy to formalize ideas, but the problem itself is quite easy to understand. So for example, if we have the problem, for example, that A and B um, are natural numbers, and they satisfy the property that A divides B square and B square divides A cube and A cube divides B to the power 4 and so on. And you want to show that A equals B. So already VP is very helpful because first of all, uh, if A divides B, then can we try and relate VP of A and VP of B for any prime P?
Like
Can,
for all primes, VP of A must be less than 2 times VP of B. Then for the next one, VP of B should be 2 VP of B should be less than 3 VPA.
yeah, you're close enough. It should be like VP of A would be less than or equal to 2 VP of B, right?
Yeah, that's what I meant. Yeah.
Yes. So we have VP of A is less than or equal to 2 VP of B. That's less than or equal to 3 VP of A, and so on. So like, can we try and relate VP of A and VP of B like this? Like, can you like, so we have for any odd number n, we have n VP of A is less than or equal to n plus 1 times VP of B, right? Um, and that would give us that VP of A by VP of B is less than or equal to n by n plus 1 for any n, for any odd n, right? But then we also have, can anyone say like if n is an even number, how do we like bound VP of B by VP of A? Um, Anyone can say. Sanskar says.
Yes, hello.
Yes. So if n is an even number, how do you relate VP of B by VP of A?
Like, just like put 2k and equal to 2. Like, what do you mean? Like, you can take the limit n to infinity, right?
Yes. So like you have this, and then like you have 2 VP of B is less than or equal to 3 VP of A and all that, right?
Yes.
So like if n is even, you have n VP of B is less than or equal to n plus 1 VP of A.
Yes.
Right. So then like what do you do after that?
So like you can first bound it between two numbers. So for even you would have the opposite true. And then you will like get two expressions whose both limit at infinity would be one. So by like it will be bounded between one and one. So the ratio would actually be equal to one. Like yes.
Yes, exactly. That's how it is.
Yeah.
So can you like formalize it?
Like n and n plus one, like this is like greater than equal to n plus n by n plus one, and it's less than equal to n plus one by n. So if you take the limit to infinity, then you'll get it's less than equal to one on one side and greater than equal to one on the other.
Yes. Okay. Great. So this means that so like we've basically shown that what is this? Yeah, VP of A by VP of B is less than or equal to some number. That is a function of n, and as n tends to infinity, that function tends to 1,
Yeah.
which means that VP of A by VP of B is less than or equal to 1. But then VP of B by VP of A is shown to be less than or equal to another function of n, the reciprocal, which also tends to 1 as n tends to infinity, which means that VP of B by VP of A is also less than or equal to 1. That would imply that VP of A is equal to VP of B. But now, note that this holds for all P prime, right?
Yes. So that means a equal plus minus b.
Exactly. But we've defined A in positive integers, so like you don't need the plus or minus.
Okay. A equal b.
Um, yes. So now with this VP definition, can anyone tell me how you would write the prime factorization of a number n?
Like just p to the vp product.
Exactly. N is equal to product p to the power VP of n. I hope everyone knows this symbol, or shall I explain it? Like, is there anyone who hasn't seen this symbol before? Um, there aren't a lot of people. Okay, you haven't seen this.
He probably means he's seen it. Like he's yes.
All right. Never mind then. Yes. So this is how the prime factorization of a number can be written, and this is helpful in a lot of construction problems. Um, um, where you want to sort where like for example, if you want to look at the number of divisors of n, this is very helpful. Okay. So now this is just like the definition of VP and everything, but so now let's like get to some properties of VP. So like say we have um okay, properties. Let's say we have x and y in natural numbers. How do we write VP of xy?
Vp of x plus vp of y.
Yes. Can someone who hasn't seen this before, can you like show this? Can you like prove this for me? Has anyone not seen this before? Okay, I guess not. Okay, fine. I'll just, what happened to now? Nothing much. We just defined the VP function. Um, that's the largest prime exponent in n. Um, so essentially, VP of n would be the largest prime exponent dividing n. So it's the number at the top. And then we just solved a problem using VP, a very simple problem. Um, so this is the problem. You can take a screenshot if you want and try to solve it later. Um, and now I'm just getting to the properties of VP, right? So how do I show this? So essentially, I can write x is equal to product p prime as of p to the power vp of x, and I can write y is equal to product p to the power vp of y. And I can write xy is equal to product p prime p to the power vp of xy. But note, this is also equal to product p prime um, p to the power vp of x plus vp of y. And since all the primes are co-prime to each other, we can say vp of xy is equal to vp of x plus vp of y. Great. Now we can come to addition as well. Um, can anyone tell me like what vp of x plus y would be? In fact, let's forget about p for now, and let's just look at v2 of x plus y. Okay. Can anyone tell me what this would be if you want? Like, I want someone who hasn't seen this before to like try to figure out what it would be, is all. Um, do I have to call out names then? Um, can someone speak up because it's okay. You know what, Aritra, go ahead.
It will be like minimum of v2 of x and minimum of v2 of y,
Yes, and
greater than equal to.
yeah, and when is it equal?
When they have different v2s, that will be equal. And in the case of v2, it will be strictly greater than if
Yeah,
they are equal.
right. So now I'm just gonna go ahead and prove this. And then someone else can try to figure out VP of x plus y in general. So the point is, if V2 of x is not equal to y, let us say V2 of x is equal to a, V2 of y is equal to b. This is the simple stuff. Okay, this is the thing everyone would do. So x would be equal to 2 power a times k, where k is an odd number, and y would be equal to 2 power b times l, where l is an odd number. Okay, and in the case 1, let's assume that a is not equal to b. Well, then what happens? We can, without loss of generality, assume um, that a is less than b. Right? Why can we assume this? Because the other case is symmetric. Now, if we want to add x plus y, it's just 2 power a times k plus 2 power b times l. That would be equal to 2 power a times k plus 2 power b minus a times l. We're almost done. Why is this odd? Can anyone tell me why this thing is odd?
Like 2 divides the second part and 2 does not divide k. So GCD of k and that will be 1. Like k and
Exactly. Exactly. Because this is odd and this is even. Therefore, this must be odd. And this is well 2 power a. So that means that v2 of x plus y is equal to a. And that's just min of v2 of x comma v2 of y. Great. What if a is equal to b? What happens if a is equal to b? Ahan, you can.
yeah, like if they are equal, then we cannot say now like if k and like now k plus l will have to be even.
Yes,
So it will be greater than that.
yeah, exactly. So v2 of x plus y is greater than a, right? Because odd plus odd is even. Now we can't say anything really about the exact value of this v2 Because for example, I could have k is equal to 1 and L is equal to 3, in which case the V2 would be like a plus 2. But maybe k is equal to 1 and L is equal to 7. And in that case, V2 would be equal to a plus 3. Um, so we cannot say anything about the exact value, but we can definitely get some inequalities, and these can be very helpful in problems. If people want buffers, wait, I'll send a buffer. Right, right. So yes, I hope everyone got the buffer. Um, so like yes, we've now just defined the basic properties of VP, and we can in fact do more. What do you think the VP of x plus y would be, like for a general prime? Again, we can divide this into two cases. If VP of x is not equal to VP of y, what happens?
Proceeding by the same logic we get, it must be the minimum of them.
Exactly. VP of x plus y would be equal to min of VP of x comma VP of y. And what if VP of x was equal to VP of y?
This is similar to the previous one, but like now we cannot know that if k plus l, if p divides k plus l or not. So there's an equality case also involved. Like there's a greater than equal.
Yes. So we get that VP of x plus y is greater than or equal to min of VP of x comma VP of y. The main reason is that k plus l may or may not be divisible by p. All right, it's going down. Right. So now this is one important thing to note, because if I have VP of x plus y greater than or equal to min of VP of x comma VP of y, the important thing is that the equality holds when VP of x is equal to VP of y. Like if VP of x is equal to VP of y, then the equality will hold. But if VP of x is not equal to VP of y, then the equality may or may not hold. But if P is equal to 2 and VP of x is not equal to VP of y, then the equality can never, sorry, what? If P is equal to 2 and VP of x is not equal to VP of y, then the equality holds. But if it is equal, then the inequality would hold. I'll just write it down to make it clear. If P equals to VP of x equals VP of y, um, equality, and if it is equal, then it's just greater than or equal to, we can't say anything. So now this thing, this separate thing, like if P is not equal to 2, then if VP of x is equal to VP of y implies greater than or equal to, but if P is equal to 2, it's only greater than. That's a very important thing. And in problems where you're using VP and does addition and stuff, um you can often use V2 to get some strict inequalities, and that helps a lot. Okay, so we'll now do another problem. So so find all integers. Uh, okay, positive integers that can be represented in the form LCM of x comma y plus LCM of y comma z over LCM of x comma z. So in this problem, we're going to figure out what the VP of GCD and LCM are, and using that, we're going to solve this problem. So first of all, any ideas on GCD and LCM, like what their VP would be?
It's the min of the two.
Yeah, exactly. Min of VP of x comma VP of y, and LCM would be what?
The
LCM,
max.
yeah, LCM would be max. Yes. And now let us go back to this problem. This is problem we have. So like what ideas do you have? Okay, one thing is that if you have an expression and you want to analyze it, you can try and look at what variables it is symmetric in. So for example, this expression, like if I swap x and z, I get the exact same expression back. So now if I have something like that, if an expression is symmetric in x and y, then often plugging in x equals y gives me a very useful thing. So so what happens if I plug in x equals z? Come on, like just plug in x equals z and see what happens.
You get an integer.
Yes, but like what kind of integer? Okay, wait, you know what? I'll just write it down. You get LCM, okay, 2 LCM of y comma z over LCM of z comma z is just z. Now, note that z divides LCM of y comma z, right? This means that this part alone is an integer, and this whole thing is just 2 times an integer, which means that we obtain an even integer, right? So now we have that all even integers are can be expressed in this form, right? You just like have to put y is equal to kz, k times z, and the expression becomes 2k. Now, what do you think? Like, do you think we can express odd integers in this form? Anyone?
Oh, no, because there's a 2.
Exactly. But what if x is not equal to z? What happens? Like, can I?
Okay.
Yeah, go ahead.
Can we take cases on we can take like without loss of generative, we can switch x and j. So
Yeah.
can we take cases of what v2y is like
Yes.
v2 of
Exactly. First of all, why v2 at all, right? Because we want to show, we want to try and show that odd integers, we want to try like and represent odd integers in this form, or maybe we want to show that odd integers cannot be represented in this form, right? Which makes us want to show, which makes us want to find x, y, and z so that this is equal to 0, right? And which is why we take v2 at all. So now I'll just move down. So we want to show, we want to find x, y, and z such that v2 of x plus what? Oh my god. Never mind. Yeah, v2 of LCM of x comma y plus LCM of y comma z is sorry, minus v2 of LCM of x comma z is equal to 0, right? Now what is this equal to? Like, I know this is equal to what, max of v2 of x comma v2 of z. What would this be? Someone? Give me 2 minutes.
I guess it would be maximum v2 of x, y plus maximum v2 of y and z.
Sorry, could you repeat?
I guess it would be the maximum v2 in x or y plus maximum v2 of y and z.
Yes. And can you use the addition thing we did earlier? Yes. So like, what would this be? This would just be like, can you hear me?
Yeah.
you are audible, I think.
Okay. Yeah, this would just be like greater than or equal to minimum of max of x comma y and max of y comma z, right? Is everyone fine with that? So we essentially want to find x, y, and z such that um, such that 0 is greater than or equal to the min of max a comma b. What? Uh, let's just, okay, my bad. I made a mistake. Let's just write a equals v2 of x, b equals v2 of y, c equals v2 of z, my bad. So we want to find a, b, and c such that 0 is greater than or equal to minimum of max of a comma b, comma max of b comma c, minus max of a comma c, and equality should hold if and only if max of a comma b is not equal to max of b comma c, right? And that gives us two cases, right? um One case is max of a comma b is not equal to max of b comma c. What happens in this?
Then like the equality holds.
Yeah, but like what so like we have, okay, yeah, fine, equality holds where minimum of max of a.
And B lies between A and C.
Okay, why is that true? Like why can't we assume that b is greater than or equal to both of them? You're right, but like why can't we assume that?
Like if B was the greatest, then both would have to be B.
Yes, and so b would be equal to max of a comma c. But that would give, what would that give us?
Like like the 0 would not have been greater, right? Since
Yes,
max of A
exactly.
comma C would be less.
Exactly. First of all, if b was greater than or equal to both of them, then max of a comma b would be equal to max of b comma c. That's a contradiction to this, right? So that means we must have either a is less than or equal to b is less than or equal to c, or b is less than or equal to a and c. Okay, what happens now? What happens in this case? B equals c. Um, okay, yes. And why is that? Because max of A and B is B and max of B and C is C. Exactly, exactly. But B equals to C implies that um, max of A comma B is equal to max of B comma C, and that's a problem, right? Also a contradiction, which leaves us with this case: B is less than or equal to A and C. What happens then?
Here
We can,
equality holds, like
Yes,
minimum of max of, like that expression becomes greater of the two, or two of A and C, and minus maximum of A and C.
yes. But like, why is that a contradiction? Wait, what did you say? Could you repeat once? I didn't quite get.
Like then equality holds, right?
Yes, equality holds above, right? In this one. This is what you mean, right? Equality in this one.
No, like 0 is equals to,
Oh, that. Yes.
no, wait, no, sorry.
Wait, what?
we can, without loss of generality, assume A less than equals to C because we can interchange X and Y.
I'm sorry, your voice is breaking. Can you repeat?
Like basically we have that the above expression where 0 is greater than equals to, we get that 0 is greater than equals to the minimum of A comma C minus the maximum of A comma C, but that is a contradiction. So A has to be equal to C.
Yes, exactly. Um, Another way to see that would be like min of A comma C would be equal to max of A comma C, right? Therefore, A is equal to C. Simple. I think this is what you said. Just said it in simple.
Yeah,
Yes. And again, this is not possible, right? So we that means the first case is a contradiction, and so we must have max of A comma B is equal to max of B comma C. This is like our only hope now. So what happens here? Yeah, what happens here?
like if B is like B lies between A and C, then all have to be equal.
Yes, this gives A is equal to what? Max of A and B, and that's equal to max of B and C, and this is equal to B. This is a problem, right? Um, then what is the next case? Sub case.
Again, if B is less than C, like B is less than both A and C, then A equals to C must hold.
Yes, this case gives A equals C. Mm, yeah. What about B greater than or equal to A comma C? Um, Anyone? Just keep this thing in mind. Um, this one. This is the main thing, and we just like we're trying to contradict this at all steps. If B is greater than or equal to A comma C, what happens?
This holds, right?
Um, why? Because max of A comma B is equal to B, and max of B comma C is also equal to B. So the minimum would be B. So that gives us 0 is greater than or equal to B minus max of A comma C, right?
Yeah.
Okay, great. So we have, one sec. This gives us 0 is greater than or equal to B minus max of A comma C. Um, so now, can you try to show that this thing is less than or equal to 0? Like with some above property. Like basically, you have max of A comma B equals max of B comma C satisfied, right?
Yeah.
What else can you do?
We have got that 0 is greater than equals B minus max of A comma C, but B is greater than max of A comma C. So we must hold that B minus max of A comma C is greater than equals 0.
Yes. So this would imply that B is equal to max of A comma C, isn't it?
Yes.
And that would imply that without loss of generality, we can assume A is equal to B. right?
Yes.
And then what? This would just give us max of a comma b. Sorry, what? No, this would give the LCM values. The V2 of the LCM values would both be a and b.
Yeah, so it would be equal to 0, but since they are equal, it must be greater, strictly greater.
Yes. This would imply that like b is greater than c. Sorry, what? What did I write? Yeah. This would imply that b is greater than c, but like that's a problem because then max of a comma b would be. Oh, that's not a problem. Wait. Oh, the LCM values would give a contradiction. Right. Right. So that means that we cannot have that particular V2 like what is going on? Yeah, so we can never satisfy this, right? Like given A, B, and C in non-negative integers, we can never satisfy this um, with the equality holding if and only if this is true. So that means that odd integers cannot be represented in this way, and so the only integers that can be represented in the form LCM of x comma y plus LCM of y comma z divided by LCM of x comma z, they're just even integers, right? And we had the construction above. What was it? K um, x equals z equals k, and y equals nk works, where n is some natural number. Has everyone got this?
Yeah.
All right.
Yes.
Yeah.
Does anyone have any doubts before we proceed? Yes? No? All right, then I'll proceed. Um, now we'll come to the factorial um, formula. So essentially, we want to find VP of n factorial. Like, can anyone tell me like how we would approach such a problem?
You can first find the number of multiples of p which are less than n.
Yes, and how many are there?
Gif of n by p.
Yes. So first, the number of p floor of n by p. And why is this so?
Because
We can just write down the division algorithm.
Yes, exactly. It's just like n is equal to pq plus r, where 0 is less than or equal to r is less than p, and then we can write q is equal to n minus r by p, and that would just be floor of n by p. Great. Now, if we have p square over here, this is just floor of n by p square, right?
yeah, and we have to repeat that because we need 2 for p square.
Yes, exactly. So now say I have n factorial, right? It's like 1 into 2. In fact, I'll be more concrete and I'll say 20 factorial. Okay. This is like 1 into 2 into 3. I'll just write it out. 8 into 9 into 10, 12, 13 into 14 into 15 into So say we want to find like v2 of 20 factorial, right? What happens? So we can first of all remove all the odd numbers, right? Why can we do that? Because the odd numbers do not contribute a power of 2. Now, if we look at just the even numbers, each even number contributes exactly at least one power of 1, right? So, for example, 2 contributes a power of 1, 4 contributes 2 powers of 1, 6 contributes another power of 1, and so on. So, like each number, each even number contributes a power of 1. That's already 20 by a floor of 20 by 2 powers of 2. But we're not done yet. We've actually undercounted because there are some numbers that contribute more than 1 power of 2. Those are, for example, the multiples of 4, like 4 contributes 2 powers of 2, 8 contributes 3 powers of 2, etc. So to count that, we count the number of multiples of 4. So they add an extra power of 2. So for example, the number 12 is counted in this because 12 contributes 1 power of 2 in this part, and 12 contributes another power of 2 in this part because 12 is a multiple of 4. Then but we're still not done, right? Because we haven't counted the multiple of 8s or multiples of 8, and we can go on like this forever. So the final formula we get is vp of n factorial is equal to summation p equals 1 all the way till infinity, floor of n by p to the power, sorry, wait a minute, I, floor of n by p to the power I. Now, this is an infinite sum, right? So like, isn't VP of n factorial finite? Like, why is this an infinite sum but it's going to a finite number?
Like the moment
Because
p power I crosses n, all the subsequent terms become 0.
Yes, exactly. When p power I, when p power I is greater than n, we'll have floor of n by p power I is equal to 0. And this is satisfied for all sufficiently large I, right? Sufficiently large I. So, that would mean that there are only finitely many I, such that this floor of n by p power I is non-zero. So that would finish. That would show that this is finite. So has everyone understood everything till here?
Yes.
Yes, sir.
All right. Um,
Sir, I have a question.
all right. Don't call me sir, please. But like,
Like how did like how we did before, similarly can we find v of x plus y n factorial?
yes, of course. So like v p of x plus y factorial. That would be like, you don't even need the VP of x plus y formula. You can just directly write this is summation floor of x plus y by p power I. I equals 1 to infinity. Right? Um, did everyone get this? So like we don't even need to use the VP of x plus y formula over here. Have you understood?
Yes.
Okay. Now there is another very useful formula for n factorial. And essentially the way it's defined is if I consider the base p representation of n. So like if I write n is equal to what? P, I know, n k minus 1 and 2 and 1 and 0 p. And so this is just the base p representation of p. Then if I define Sn as the sum of the digits of p in the base p representations, this would be Sn would be like nk plus nk minus 1 and so on. Then I can define I can prove that VP of n factorial, sorry, I've used wrong notation, my bad. Um, I'll write this instead as SP of n. Okay, this makes more sense. I can prove that VP of n factorial is equal to n minus SP of n over p minus 1. Okay, this is also like this is quite similar to the sum of floors formula we proved earlier, and it's also a lot more useful because now we can see that V2 of n factorial, for example, would be n minus S2 of n. All right. So this is one very useful thing. And I'll probably put this in the P set or something. I don't know, but this is not very hard to prove, and it would be very useful for you to prove this by yourself. So yeah. Does anyone want a buffer or?
What is S2 of n again?
Oh, S2 of n. So like over here, I defined base P representation of n, right? Like you're familiar with bases and all, right? Base.
Yeah, yeah.
Yes. So if I write n in base 2 and I take the sum of its digits, that is defined as S2 of n. I wrote SP of n over here.
Okay.
So S2 of n would be the sum of the digits of n in base 2. Did you get that?
Yeah, I got it. Thank you.
Yeah, sure. Great. So no one wants buffers? Okay, fine. Then let's do another problem on VP. So, okay. So, do you want to do a Diophantine or do you want to like to prove some sort of, do you want to like directly use VP in something? Okay, wait, I will put up two problems. Um, okay, Diophantine, sure. Um, let us do the following problem. P3. Find all pairs k to the k and n in positive integers such that k factorial is equal to 2 power n minus 1 times 2 power n minus 2 so on till 2 power n minus 2 power n minus 1. Okay, I'll give you some time to think. Okay, first of all, think about why you would even want to use V2 in this or VP in general. Anyone, any idea?
We would use V2 as in the RHS. The V2 of that side is 2 only.
Um,
1. 1, sorry.
it's not one or two. Like you have a bunch of products, right?
Like it will be 0 plus 1 all the way up till n minus 1.
Yes, exactly. If I consider the V2 of this, it will be like 0 plus 1 till n minus 1. And if you think about it, that's like a very large VP, right? Like if you think about this, and also these numbers are quite spread out, right? And they'll have a lot of like different prime factors. So that's what makes us think about like VP. Now, can we try and find all k such that V2 of k factorial is equal to this thing, n minus 1 times n by 2, whatever.
What was the question?
You want to find all k and n such
No,
that.
I got that. Like just now you told something.
Oh, okay. Can you like try and it's just the same question. Just I just reformulated it. Can you find all k such that v2 of k factorial is equal to um 0 plus 1 till n minus 1?
Okay. K equals 2 power n works, I guess.
K equals to power n. Well, that's quite big because like if k is equal to 2 power n, then 2 power n is counted in the left side, right? But like 2 power n is larger than, like, how should I say this? Like v2, wait, let me explain. Give me a second.
Oh wait,
Give
never
an
mind.
example of 2 power n working.
No, I made a mistake. So
Okay, never mind. Okay, see, one thing is that v2 of k factorial is is equal to k minus s2 of k, right? And this is obviously less than or equal to, no, sorry, less than k, right? Does everyone understand that? v2 of k factorial is less than k. Everyone
Yeah.
understands this, right? Great. This means that k is greater than v2 of k factorial, which is greater than, sorry, which is equal to v2 of RHS, which is equal to n times n minus 1 by 2, right?
Yes.
Okay. So we have this. Now what do we do? Okay. Another thing you can note is that 2 power n is greater than each one of these terms, right? 2 power n is greater than this, 2 power n is greater than this, so on, right? So can you like try to bound this, the RHS somehow? Like can you show it's less than or equal, less than something? Anyone?
It's less than 2 to the power n.
Yes, but each term is less than 2 power n, right? And there are n terms. So the whole product is less than?
2 power n square.
Yes, exactly. Exactly. So 2 power n square is greater than the RHS, right? And the RHS is equal to k factorial. And k is greater than n into n minus 1 by 2. How do we use this bound now? Can anyone like, how do we compare k factorial with something based on k greater than this thing? Anyone? Like just think about it. Like k is greater than n into n minus 1 by 2. So k factorial is greater than?
Like n into n minus 1 by 2 factorial.
Yes, that's it. N into n minus 1 by 2 factorial. Yes. And now we're not really done, right? Because we haven't really gotten a contradiction. Now, what is, can we show this is greater than or equal to something? Like there is, we've got 2 power something on the left side, right? So naturally we want to show that this is greater than some other power of 2, because then we can take log on both sides and we'd get like the exponent, like n square is greater than the other exponent. So can we show that this is greater than or equal to some power of 2? So first of all, we have this is equal to 1 into 2 into 3 into so on, right? So I can now say that this is greater than or equal to 1 into 2 into 2 into 4 into 4 into 4, um,
Yeah.
into 4 into so on, right? But that does not really give me a good bound, because what is this? This is like 2 power n square greater than or equal to 2 square into 2 to the power 2 times what? N square minus n by 3 minus 3 by 2. Worry about the handwriting, which is 2 power n square minus n minus 1. That's obviously true, right? So like we'll need a better bound.
Yeah.
After this, what can we do? Can we like start putting 8s over here? I hope everyone understands why we're doing this, right? Like more than what we're doing. I hope everyone understands why we're doing this.
This
Right?
is greater than um
Just 1 second. I just erased this stuff. Yes. Go ahead.
this is greater than this thing 2 power v to this thing.
Sorry, could you repeat? Your voice is not clear.
I'll write on the slide.
Okay, yeah, sure.
We can keep doing this.
Like I think what is this equal to? So we have like two twos. So we have like one in the beginning, two twos, four fours, and then the rest are eights, right? Yes, sure, we can also do that. But like we cannot really do much with v2 of n into n minus 1 by 2, right? um because that's like not a very easy expression to handle. So like, okay, fine, I'll just go ahead and say it. This is 2 square into 2, 2, 2, 3, what, n square minus n minus 12. Okay, and what, this is like 2 power 2 plus 8, that's like 10, plus 3n square minus 3n minus 36 by 2, and let's just add this. So we get n square greater than 3n square minus 3n minus 16 by 2. So like when does this hold? When does this hold? First of all, take this side. So we want n square minus 3n minus 16 less than 0. Okay, when does this hold?
Hello.
Yes.
In the above equation, how did you get 2 cube times n square minus n minus 12 by 2?
Yes. So we have 1 over here, right? We have two twos, and then we have four fours, right?
Yes.
Okay, my bad. This is 14. Uh, yes. So we have these 7 terms, and then the total number of terms is n square minus n by 2, right?
Yes.
Be n square minus n minus 2, n square minus n by 2 minus 7, okay, right?
Yes.
And that's just n square minus n minus 14 by 2.
Thank you.
Yes. Okay, I have to fix this then. 2, 8, 10, 3n square minus 3n minus 42 by 2. So this would be like minus 22 by 2, right? So we have this over here. Okay. And then this can actually be checked by hand. This holds only for n less than 7. Okay, and n less than 6, we can just check it by hand. Okay. I'll probably put this as well on your P set, just like for writing up, as well as to check n less than 6 by hand. Okay, great. So what, we have 15 minutes left. Okay, so I can cover another theorem now, and maybe I'll solve another problem after that. But first, I want you guys to find out v3 of 4 to the power 3 power n minus 1. Okay, like I just put this out of nowhere and I want you to find this out. Okay, like given n, I want you to find this out. Like, can you find this in terms of n? Like, let's just do this because we don't have so much time. So if n is equal to 0, what happens? This becomes v3 of 4 to the power 1 minus 1. That's equal to v3 of 3. That's equal to 1. N equals 1 gives what? v3 of 4 to the power 3 minus 1. That's v3 of 63, which is equal to 2. Already you can see a pattern, right? What's the pattern here?
Like the expression is equals to n plus 1.
Yes, exactly. So can we conjecture that this is in general equal to n plus 1 and then try to prove it? So for that, first of all, let me tell you a theorem, okay? Because we don't have much time to show this. I will tell you a theorem, and we'll prove that instead, and then we can show this afterwards. So if p is odd, this is known as lifting the exponent. If p is odd, given a and b in naturals such that p divides a minus b and p does not divide a or b, and you have a natural number n, then um, we have vp of a power n minus b power n is equal to vp of a minus b plus n. Okay, sorry, not n, vp of n. Okay, so first of all, if n, okay, and not, if n is equal to 1, okay, not n, not, wait, what? Yeah, n. So if n is equal to 1, what happens? Can anyone tell me?
Like it just asks us to show that vp of a minus b is equals vp of a minus b.
Exactly. So that gives us an idea. Let's try and prove this by induction, right? So, but we can't really do much with this case, right? Because um, it does not really help much with the induction step. Now note that if I have vp of a power p power k minus b power p power k, is equal to VP of A minus B plus K, right? Then if I want to show that VP of A par P par K plus 1 minus B par P par K plus 1 is equal to VP of A par P par K to the power P minus B par P par K to the power P. If I can show this statement for n equals P, then it would be pretty nice, right? Because then I can write that this is A par P par K minus B par P par K plus VP of P, which would be 1. And this is given here. So it's like VP of A minus B plus K plus 1. Does everyone understand what I've done here?
Yeah.
So that motivates us to try and prove this statement for just n equals P, because then we'll be done, right? So we want to just prove.
What you've done in the last step.
Oh, okay. So here I have assumed this thing, VP of, so we're just trying to prove the statement using induction. Okay. So I have assumed this thing and I'm trying to show that this is equal to this. Okay.
Okay.
Now, do you understand how I've gone this way? If n equals P works, then I can do this, right?
Yeah, I get.
Now, if I want to go from here to here, basically I just used my assumption over here. VP of A par P par K minus B par P par K is equal to VP of A minus B plus K, right? We assume this.
Okay.
So I just replace this thing with this thing.
Okay, yeah, got it.
Yeah, great. So we just now want to show that VP of A par P minus B par P is equal to VP of A minus B plus 1. Now, A par P minus B par P is divisible by A minus B. So we want to show that V par P of A par P, sorry, VP of A par P minus B par P over A minus B is equal to 1. This is equivalent, what is A par P minus B par P over A minus B?
Like A par P minus 1 plus B times A par P minus 2 and so on till
Yes.
B par P minus.
Yes. What? It's glitching. Just hoping. What's going on? Yeah. So we have this. We want to show this. How do we show this? So remember what we are given. We are given that P divides A minus B. P does not divide A or B. Okay. So how do we show this? So first of all, what is P divides A minus B equivalent to? It is equivalent to A is congruent to B mod P, right?
Yeah.
So then what would this be mod P?
There are P terms, so it would be P times A par P minus 1.
A par P.
No, A par P minus 1.
Okay, great. So it's like P times A par P. Yes, great. P times A par P minus 1. Yes, so this is clearly divisible by P. Now we want to show that this is not divisible by P square, right? How do we do that? Ideas?
Like if it is divisible by P square, then we would have like A par P minus 1 is also divisible by P, right?
No. We already know that P does not divide A. So A par P minus 1 cannot be divisible by P. No. The idea is that A is congruent to B mod P, right? So you write B is congruent to A plus PK. Or in fact, B is equal to A plus PK. Okay. And then you can do stuff because Then you have summation a par k b par p minus 1 minus k. K is equal to what? 0 to p minus 1, right? And this would be equal to k equals 0 to p minus 1 a par k a plus pk to the power p minus 1 minus k. Everyone gets this?
Yeah.
Yes, great. Now can we say that this is congruent to something mod you know p square? We want to show that this is non-zero mod p square. How do we show that? Okay, we can just use the binomial theorem, right? And then remove stuff mod p square. So this would be like a par k times what? A par p minus 1 minus k plus p times a par p minus 1 minus k minus 1 oops, times pk, right? That's it, because the rest of the terms would have pk raised to the power 2 or more, and that would already have p square times something. But this second term also has p square times something, so we can remove that as well. So this is just congruent to like k is 0 to p minus 1 e to the power p minus 1, and this is equal to pa power p minus 1 mod p square. And this is where we use the thing that p does not divide a, right? Because now a power p minus 1 is not divisible by p, which means that this cannot be 0 mod p square. Yes, it is 0 mod p, but it cannot be 0 mod p square. Does everyone understand this? We have basically just proved LTE. Okay, like, does everyone understand that?
Yes.
Great, great. So now using LTE, can anyone tell me what this would be? First, I want you to like recall the conditions for LTE. What are the conditions in this problem?
So 3 is a prime, right? And then we have 4 minus 1. They are both natural. And 3 divides none of 4 and 1. And 3 divides 4 minus 1.
Great. So then what? So now we can apply LTE. So
So
what?
yeah, we are free to apply LT, and after applying LT, we see this is equal to V3 of 3, that is 1,
Yes.
plus V3 of 3 power n, that is n.
Yes. Great. So we're done. That's n plus 1. Great. So now we have like 5 minutes, but like if you can, do you want to do, okay, fine. I'll just give one problem. So we basically, in this one, we are given a natural number k, okay, and we define sk as the set of all triplets n comma a comma b such that n odd gcd of a comma b is equal to 1, a plus b is equal to k, and n divides a power n plus b power n. Okay, we have to find all values of k such that sk is finite. Okay, does everyone understand the problem statement? Okay, another thing we can do with LTE is when n is odd, we can write vp of a power n plus b power n is equal to vp of a power n minus b to the power n. Okay, so this would be like what? Vp of a plus b plus vp of n when n odd, p divides a plus b, p does not divide a or minus b. Okay, did everyone understand this one?
Yes.
Great. Okay, now for this problem, I'll just walk you through the solution and maybe I'll put it in the P set. Okay. So the idea is that if k is odd, then there exists an odd prime dividing k, right?
Yes.
Yeah. And so then we can try VP of a power n plus b power n. Because n is odd, we can apply LTE, right? And p does not divide a plus b, and the GCD is 1, so p cannot divide both of them. So VP of a power n plus b power n is equal to VP of a plus b plus n. Sorry, VP of n, right? But this is obviously greater than or equal to VP of n, right? Which means that, um, one sec. Which means that if n is a power of p, then n must divide a power n plus b power n. Sorry, not k, m. Did you understand that? Did everyone understood?
Yeah.
Great. This means that there exist infinitely many n such that n divides a power n plus b power n, right? And that means that k must not be odd. In fact, k must not have an odd prime factor, right? Because then we can construct infinitely many n such that this thing is satisfied, which means that k must be a power of 2. Okay. Since the class time is getting over, I guess I will put this case in your P set. But I will give you a hint that all powers of 2 work. And another hint I can give is that you can try and use orders to prove it. Okay, there's no VP used in this. You can try and use orders to prove this. I will also put, you also must note that in the statement of LTE, I had stated that P is odd. So we have a sort of problem if P is equal to 2, because then one second, I'll just drop that. Because then the statement of LTE becomes much more complicated. So essentially over there, the statement is that 2 divides a minus b and a, b are odd. Then V2 of a power n minus b power n is equal to, and also n is even, is equal to, this is equal to V2 of a square minus b square plus V2 of n by 2. Okay. And this is also not very hard to prove. It's just like the um, proof for LTE when P is odd. This is also going in your P set, I guess. So you can prove this, and maybe if you want, you can send me your proofs and I'll check it for you. So does anyone have any doubts? Hello?
No.
Okay, a p-adic representation. Okay, that goes into analysis. You can check Evan's blog on that. That covers it very nicely. But it's far too complex for this class. I'll just send the link in the chat. 1 second. Right. So you can refer to this link, and also there's a chapter in Evan's book Napkin. I think chapter 28 or something. In that he covers VP and p-adic stuff very nicely. So you can check that. So and class is over. I guess you can leave.